So significant figures. Basically the idea is to use sig figs to report your numbers and imply their precision. So if somebody was going to hand in an answer to a question or to a lab, writing down this number 1.40237924 meters, that seems really, really precise and really, really well known. Right? But maybe you didn't mean it that precise and well known, so you might just report it as 1.4 meters. So it's basically just rounding to imply the right amount of precision. So first we have to kind of even know how to count sig figs to be able to talk about it. So let's start with a number with a bunch of extra zeros everywhere. So my example here is 301.208000 seconds. All right, leading zeros are not counted as significant. They're just considered to be placeholders. And these aren't even important placeholders. These don't need to be written at all. So they're not significant. Zeros between numbers are going to be considered significant. They're going to be implied to be measured or implied to be reasonable and known. And if there's zeros that are included after the decimal and after all of your digits, they're also going to be implied to be significant, implied to be measured and well known. Right? For a number like 38,000 written this way, and there's no little decimal put back here or anything, I'm just going to assume then that it's roughly 38,000. So then I would count the 3 and the 8 as significant, and these zeros back here as just placeholders. Now if you wanted all of these to be considered significant, and basically meaning it is 38,000, and I know all of these zeros very precisely. So it's not roughly 38,000, it is 38,000. You could write it this way. You could write it in scientific notation. But I suppose an easier way to do that would just be to put a decimal back here. And if you put a decimal right here, I would assume then that all of these digits were well known. For actual measured data, you want to give as many significant figures as possible. And that might even mean estimating the last digit or estimating between the markings on a meter stick. All right, so for measured data, give as many as possible. But then for results from that, for calculated values coming from that data, you want to round your final answers. And we're going to introduce a couple of rules for doing that. But I do suggest that you don't round until you've finished all your math. So you could do your homework or your lab and keep some extra digits. And then when you're all done with the problem on the homework or you're all done with the lab, then go back and then round. So here's a rule for rounding for sig figs after multiplying and dividing. You want to keep the least number of sig figs as your input information had. So as an example, how about we do 30.0 divided by 6.0. And 30.0 is known to 3 sig figs, 1, 2, 3. And 6.0 is 2 sig figs, 1, 2. So our answer is 5. But we should show that answer to the least well-known sig figs. Right, so 2 sig figs here is less well-known than the 3 sig figs here. So we want to show that value of 5 to 2 sig figs. So I would do 5.0 as my final answer. Now if we did 3.20 times 3.14159, I would say that this is known to 3 sig figs, and this is known to 6 sig figs. So the 3, the 2, and the 0 are all implied to be well known and measured. The 3, 1, 4, 1, 5, and 9 are all implied to be important and measured. So then our answer from a calculator would have a lot of sig figs. All right, but we should round this to imply the precision. And the precision can't be known any better than the least precise of these. And so this was the least precise at 3 sig figs. So that means that this 0 here would either stay a 0 or round up to a 1, depending on what this next number was. And so this next number was a 5, so I'm going to round to the 0 to a 1, so 10.1. Now, so that was for multiplying and dividing. You keep the least number of sig figs. For adding and subtracting, it's a little bit different. You count significant decimal places. We're going to keep the least number of decimal places of your input values. So let's do a couple examples so you can see what that means. So if I did 100.02 minus 99, on a calculator I'd get 1.02. Now I would say that this is significant to 2 decimal places, and this is significant to 0 decimal places. So which one of those is the least well known? It's the 99. So we want to round our final answer to that same number of decimal places. So just 1. For 35.1 plus 2.777, on a calculator we would get 37.877. This is only known to 1 decimal place. This is known to 3 decimal places. So we want to round our answer to the least significant, the least well-known decimal place. So we're going to only keep 1 decimal place. So this 8 is either going to stay an 8 or round up to a 9, depending on the number behind it. So it'll be 37.9 then as our final answer.